Good evening. Before going to the topic, I would like to introduce myself. My name is Tarsam Krishna, and I have completed my post graduation in SV College of Sciences, SV University Tirupati, and I have qualified exams like National Eligibility Test, CSR Net, GATE, and APCET also. And coming to my family, I have a nuclear family. I said my parents. I have a elder brother and elder sister. They both are married. Coming to the topic, today we are going to discuss one of the important topic in organic chemistry, which is nothing but haloalkanes and haloarenes. Before going to the core topic of haloalkanes, like haloalkanes are majorly involved in two types of reactions, like substitution reactions and elimination reactions. Haloalkanes majorly nucleophilic substitution reactions are involved. Why nucleophilic substitution reactions are involved, and what is the mechanism follows like SN1, SN2, SNI, and SNNGP, and what is the effects to affect the rate of the reaction of SN1 SN2 reaction. What is the method of preparations of haloalkanes like Finkelstein reaction, Dodson reaction, Schwarz reaction? Before going to that, I would like to introduce the haloalkane. Haloalkanes and haloalkanes. Let's start with haloalkanes. What is haloalkanes? You know that already hydrocarbons. Hydrocarbons are nothing but carbon and hydrogen having compounds nothing but hydrocarbons. Alkanes are basically hydrocarbons. We will take the alkanes. What is the general formula of the alkanes? What is the general formula of the alkanes? I will take the alkanes. What is general formula of the alkanes? CN H2n plus 2. This is the general formula of alkanes. You have to remove the one hydrogen from alkane. You have to add the one halogen. You have to remove the one hydrogen of the alkanes. You should add the halogen to form a haloalkane. Simply means we know that already hydrogen and halogen have same valency, single valency. So how many number of hydrogens you have to remove, same number of halogens you should add it to form a haloalkanes. What is the general form of haloalkanes? Nothing but Cn H2n plus 1 dash. Halogens. Halogens are nothing but fluorine, bromine, and iodine. And before going to the nucleophilic substitution reactions, why haloalkanes are nucleophilic substitution reactions are involved. What we will see the what is the behavior nature of the haloalkanes. Okay, it means it behaves like electrophiles or nucleophiles. I will take one example like haloalkanes Rx. It's nothing but CH3 Cl. Okay, Rx means haloalkanes. You know that already. Halogens are more electronegative than alkyl groups. Alkyl groups nothing but carbon containing group. Halogens are more electronegative. More electronegative is what way? It takes the electrons, takes the sigma electrons, drags the electron towards the halogen to generate a partial positive charge and partial electric charge. Here halogens are more electronegative. That's why it takes the electron, sigma electron towards the halogen to form a partial negative charge and partial positive charge. Partial negative charge and partial positive charge. This is the example. Okay. Here, you know, R have a what charge you have? R is nothing but positive. Positive charge is nothing but electrophile. You know that electrophile. What is electrophile? Electrophile is nothing but electron difference species. It tends to attract the electrons. What is the nucleophile? Nucleophilic electron sufficient species. It tends to donate the electron. What is the electrophile? Electron diffusion species. What is the nucleophile? Electron sufficient species. Here alkyl group have a positive charge. That's why this one is electron deficient species. It requires electron. It needs electron. That's why outer one nucleophile. Nucleophile means electron sufficient species come and attack to the this R plus group, R partially plus group to form a bond and leaving group leave outside. Why leaving group leave outside? What is leaving group? Leaving group is nothing but it takes the sigma electrons and went outside. It's nothing but leaving group. Why it's leave outside? You know that already carbon have a 4 valency. Already carbon it forms a 4 valency. Outside nucleophile come and attack to the carbon. Carbon have a 5 valency happens. 5 valency carbon is doesn't form. That's why chlorine leaves went outside to form a bond between nucleophile and CH. This is actually nothing but nucleophilic substitution. That's why haloalkanes are mostly involved in nucleophilic reactions. Why nucleophilic reactions involved in haloalkanes are behaves like a electrophiles. Alkyl groups behaves like a electrophile because of electronegativity of halogens. Halogens electronegativity high. That's why it takes electron towards the halogen to form a partial negative charge and partial positive charge, and nucleophile attack to the partial positive charge of alkyl group to form a nucleophilic substitution reactions. Before going to the nucleophilic substitution reaction, what is the actual definition of nucleophilic substitution reaction? Let's see what is the reactivity order of the haloalkanes. What is the reactivity order of haloalkanes? I will take the haloalkanes like RF, RCl, RBr and RI. We know that already halogens are more electronegative than carbons to drag the electrons towards the fluorine to form a partial negative charge and partial positive charge. All halogens are more electronegative than carbon to form a partial negative charge and partial positive charge. Means which one is mostly fastly involved in nucleophilic substitution? It's nucleophile come and attack to the alkyl group. Nucleophile come and attack to the alkyl group. If you know that carbon have a 4 valence already, it doesn't form a 5 valency. So leaving group leave outside. What is leaving group? Leaving group is nothing but it takes the electron, sigma electron went outside is nothing but a leaving group. What is leaving group here? F minus, Cl minus, Br minus and I minus, which is involved in mostly nucleophilic substitution. How can you say which one leaves fastly from alkyl halides? Which one leaves fastly? That one involves in the most reactivity in nucleophilic substitution. How can you say that which one is leaves fastly? Which one leaves fastly means leaving group is there na? Which one is more stable in leaving group? Which one is more stable? That one is fastly leaves. Which one is more stable? That one is fastly leaves. Because that's why nucleophilic substitution reactions are more fastly involved. Which one is more leaving fastly? More stability is there. More stability leaving group is there. That one leaves fastly. So that was nucleophilic reactions are fastly involved. Reactivity is high. Which is most stable in this species in leaving group? F minus, Cl minus, Br minus, I minus is there. In that, we know that already periodic table, top to bottom size increases. Iodine have a more size. In that, negative charge is distributed in the size is high now. Iodine is size is big. So, negative charge of the iodine, negative charge is distributed. Electrons are distributed around the size. So, this is more stable. This is less stable. Why? Because of fluorine is less size. So that's why negative charge is not much distributed. So I minus is more stable. That's why he leaves from the alkyl halide fastly to form nucleophilic substitution. What is the reactivity order now? Alkyl iodide, alkyl bromide, and alkyl chloride, and alkyl fluoride. This is the reactivity order of the alkyl halides. Now we will see what is the nucleophilic substitution reactions. Actually, nucleophilic substitution reaction. Before that, what is substitution reaction? Substitution reaction is nothing but group of atoms replaced by one of the group of atoms. Nothing but substitution. What is nucleophilic substitution reaction? One of the nucleophile replace the another nucleophile is nothing but nucleophilic substitution reaction. I will take the example, we can understand easily. I will take the example CH3 CH2Cl react with OH minus. This is nucleophile. OH minus replace this Cl means what? Nucleophile. One of the nucleophile replace the one of the nucleophile is nothing but the nucleophilic substitution reaction. Whatever mechanism it follows, I will tell you later what is SN1 reaction at SN2, SN9, SNG. I will tell you later. What is nucleophilic reaction is nothing but one of the strong nucleophile replace the weak nucleophile to form a nucleophilic substitution reaction. Why strong nucleophile? You know that already. Strong nucleophiles are easily replace weak nucleophiles, but weak nucleophiles are not easily replace the strong nucleophiles. That's why strong nucleophiles are replace the weak nucleophiles in nothing but nucleophilic substitution reactions. Nucleophilic substitution reactions are followed different mechanisms like SN1, SN2, SN9 and SN and GP. What is SN1? SN1 is nothing but nucleophilic substitution reaction, unimolecular nucleophilic substitution reaction, bimolecular nucleophilic substitution reaction, intramolecular nucleophilic substitution reaction, neighboring group participation nucleophilic substitution reaction. I will discuss everyone one by one. Let's start with SN1 reaction. What is SN1 reaction? SN1 reaction is unimolecular nucleophilic substitution reaction. Unimolecular nucleophilic substitution reaction. Why it's called unimolecular nucleophilic substitution reaction? I will tell you in mechanism, you don't worry. Why it is called unimolecular substitution? I will take the one example. We can understand easily the mechanism of the SN1 reaction. This reaction also called a hydrolysis of the alkyl halides. I will take the one example like tertiary alkyl halide. I will take this is tertiary alkyl halide and this also chiral. Why it's chiral? Carbon have different groups. sp3 carbon have a different group is nothing but chiral carbon. This is tertiary alkyl halides means halide directly attached to the carbon is don't have any hydrogen. That's why this is tertiary alkyl halide. In that, you know that halogens have a lone pair electrons. Already halogens have a lone pair electrons. In the carbon around the groups like CH3, according to inductive effect, positive inductive effect, is donate the electrons to the carbon. According to plus I effect, inductive effect, donate the electrons. Here pH also electron substance species. Here also donate to the carbon. And ET means ethyl. Ethyl also donate to the electrons to the carbon. So, according to I donates carbon around the group donating to the electron towards the carbon, to carbon around the group, carbon around the electron density increases. Around the carbon, electron density group increases because of donating groups around the carbon have so donate the electrons towards the carbon to around the carbon electron density increases. Electron density increases here. Chlorine already have a lone pairs. Electron density of carbon around the carbon and halogens lone pair are repulsions. You know that electron needs to, this is repulsions happen. Repulsions happen. So chlorine couldn't stay here. So it's went outside as a leaving group. What is leaving group? It take the sigma electrons and went outside. It take the sigma electrons and went outside to form Cl minus to form a carbocation. To form a carbocation. This is called first step or rate determined step or slow step. This is called first step or rate determined step or slow step. Here carbon around the carbon electron density increases because of plus I effect. Plus I inductive effect and chlorine have lone pair electron. Electron repulsions is there. Chlorine couldn't stay here to went outside. So went outside to as a leaving group to form a carbocation. You know that Carbocation is nothing but sp2 hybridization. Sp2 hybridization planar structure. Sp2 hybridization planar structure. This is planar structure. Planar structure means you have to attack the nucleophile on both sides. You have a place. This is, if you take the planar structure like this, planar structure, carbocation sp2 hybridization planar structure. That's why if you take the second step, what is nucleophilic attack? Attack nucleophile attack. Okay? If you take a planar structure like this, you have to attack nucleophile on both top side and bottom side. You have space is there. If you take a planar structure like this, you have to attack on right side and back side, left side also. Okay? Nucleophile attacking on both sides to form two types of products. What is the product? One is retention. One is inversion. What is retention? What is inversion? It's nothing but which side leaving group leaves same side nucleophilic attack is nothing but retention. Which side leaving group leaves same side attack of nucleophile is nothing but retention. Which side leaving group leaves opposite side attack is nothing but inversion. Inversion takes place. This is racemic mixture also called. Why it's called racemic mixture? Because of 50% of retention formation and 50% of inversion formation. But here, basically, partially racemization formation. 100% racemization is not possible. Why? Because of here, two-step mechanism is there. This is second step mechanism. But first one is rate determination. Carbocation formation is the rate determination step from the haloalkanes. Okay. Tertiary halides carbocation formation is the rate determination step to form a two type of products like retention and inversion. But here partially racemization is formed. 100% racemization not formed. Why? Because of if you take nucleophile, leaving group leaves a form a carbocation. If nucleophile is there, no space, no halides are there. Backside no effect is there. Here from attacking front side some disturbance is there because of leaving group. Backside no disturbance is there. In solution we will take the reaction S1 reaction alkylates with nucleophile means water. Nucleophile is nothing but what is OH minus. Attack to the tertiary alkane. It is two-step mechanism, but in reaction is fastly move. So nucleophile attacking front side is some disturbance is there because of leaving group is there, but back side is easily attacked. So no disturbance is there. Back side is fastly attacked and to form a product. So inversion is dominate the retention. So that's why 100% racemization is not possible. Partially racemization is possible because of that's why retention is at least 40%, is 49% around. This is 51% inversion because of retention is dominate the inversion is dominate the retention. That's why partially racemization is formed. Okay, you know why it's called racemization. Say plane is there in between two. If you take the mirror, if you put the mirror in between two to form a product like this, okay, put this one, this is, if you put this molecule, this one to form a same molecule, okay, non-superimposable and but mirror image is there, is nothing but enhancement. Enhancement is nothing but racemization formation. Okay, we'll take what is the actual chemistry involved in the SN1 reaction. We'll teach it now. This is actually SN1 reaction. Now we will see what is the actual chemistry involved in the SN1 reaction. We'll take the CH2S, PH and ET. Here chlorine is there. Here the electron density around the carbon increases and chlorine have a lone pair electrons represents with there. Chlorine is couldn't stay here, went outside. But actually, chemistry is, we know that carbon halogen bond is nothing but sigma bond. According to chemical bonding, amount is the molecular orbital theory. Linear atomic combination is there. Na? Linear atomic orbital combination to form a bonding and anti-bonding orbitals. Okay, sigma bond is there. The same type of sigma star anti-bonding orbital also there. According to MOT theory, bonding orbitals and anti-bonding orbitals different energy formations, bonding orbitals and anti-bonding orbitals. If you according to hyperconjugation, sigma electrons of the CH3 donate to the sigma star of the this carbon halogen bond, sigma star of the carbon halogen. You know that already. Electrons are increases. Electrons are put into the anti-bonding orbital. Bond address decreases. Bond address decrease means bond length increases. Bond length increase means its bond is easily break. Okay, the sigma electrons donates to the sigma star of the carbon halogen bond. Sigma star increases the electron means bond address decreases. Bond address decreases means bond length increases. Bond length increase means this carbon and halogen bond is easily break to form a carbocation and second step is, you know that after formation of carbocation, nucleophilic attack on both sides and top side and bottom side or right side and left side to form a return side and inversion products. This is the actual chemistry involved in the reaction. Okay. Now we will see some important points in SN1 reaction. First one, this is two-step mechanism. Two-step mechanism. First step is carbocation formation, alkyl halide. First step is carbocation formation. Then second step is nucleophilic attack on both sides. This is two-step mechanism. First one is carbocation formation. Okay, first one is carbocation formation. This is rate determinant step. Second one, nucleophilic attacking both sides to form a retention and inversion product. This is rate of the SN1 reaction. SN1 reaction is directly proportional to the stability of carbocation. Rate of the SN1 reaction depends on the stability of the carbocation. Why? Depends upon stability of carbocation. Rate of the reaction always depends on the rate determinant step. First step, the rate determinant step. So rate determinant, what is the rate determinant step in SN1 reaction? Is nothing but formation of carbocation. Formation of carbocation means rate determinant step. So that's why stability of carbocation increases. SN1 reaction rate is increases. Then what is the second point? Here carbocation intermediate formation. Carbocation intermediate formation. Here carbocation rate of the SN1 reaction what is directly proportional to the stability of carbocation. That's why carbocation formation, carbocation is converted into less stable carbocation to more stable carbocation, like Wagner-Mervin rearrangement. Here some possibility is there. Here, if you take the one molecule, it's come to the carbocation like secondary carbocation. If possibility is there, na, secondary carbocation converting to tertiary carbocation, allylic and benzylic carbon means low stable carbocation converting to more stable carbocation, like according to Wagner-Mervin rearrangement. Here, possibility is there. So, if shifting of H minus shift, CH3 minus, hydrogen shift to methyl shift and pH shift to rearrange the carbocation. Rearrangement of carbocation possible. Rearrangement of carbocation possible. Why? Because of if you take one molecule, it's come to a secondary carbocation. This possibility is there. The secondary carbocation converted into more stable carbocation like tertiary and allylic and benzylic carbon. Chance is there. So shifting of H minus, CH minus, methyl shift and pH minus shift. Rearrangement is possible of carbocation. This is 3 point. Third point. What is the fourth point? Fourth point. What is the rate of the reaction? Why it's called unimolecular reaction? We will already tell you why it's called unimolecular reaction. What is the, according to chemical kinetics, rate of the reaction depends upon the rate determinant step. In that, in a SN1 reaction, two types of steps is there. First step is the rate determinant step, means carbocation formation is the rate determinant step. Here, according to chemical kinetics, rate of the reaction depends upon the concentration of the reactant only. Here, what is the first step? Alkyl halide. Carbocation formation is the first step, rate determinant step in SN1 reaction. This is the rate determinant step, formation of a carbocation. So, formation of carbocation rate determinant step. Though, according to chemical kinetics, reaction rate of the reaction depends upon the rate determinant step. That's why rate of the reaction depends upon the concentration of the reactant. Concentration of the rate determinant step reactant. Rate of the reaction depends upon the proportional to concentration of the reactant. What is the order of this concentration is nothing but 1. What is always rate is equal to, if you remove the proportional, take the constant form. This is what is the order of this reaction is 1. 1 is nothing but unimolecular. That's why it's called unimolecular nucleophilic substitution reaction. The rate is always depends on the rate determinant step. Rate determinant step is nothing but carbocation formation in SN1 reaction. Rate is always depends on the reactive concentration of the rate determinant step. That's why rate is directly proportional to the RCA. What is the order of the reaction is nothing but 1. What is the order of the reaction? It's nothing but 1. That's why it's called unimolecular nucleophilic substitution reaction. What is the fifth point? Fifth point, after carbocation formation, nucleophilic attack on both sides. Nucleophilic attack on both sides to form a two types of products, retention and inversion. Okay, what is the actual SN1 reaction? SN1 reaction is two types of mechanism followed. First is carbocation formation. This is the first step or rate determinant step. And after carbocation formation, any nucleophile come and attack to the both sides because of carbocation is a planar structure. Carbocation is a planar structure. So a nucleophile attacking on both sides to form two types of products, retention and inversion. So in that retention partially racemization is formed. Why? Because of front side attacking some disturbance is there because of leaving group. Back side is no disturbance is there. Slightly partially racemization is formation. Okay. After carbocation formation attacking both sides, two types of products formed. One is retention and inversion. What is the order of the reaction? Order of the reaction depends on the, according to chemical kinetics, depends on the rate determinant of the concentration of the reactant. What is the concentration of the reactant? Only depends upon the alkyl halide. Rate is only depends upon the alkyl halide. That's why this is called unimolecular nucleophilic substitution reactions. Now we will start the second one, SN2 reaction. SN2 reaction is nothing but bimolecular nucleophilic substitution reaction. Bimolecular nucleophilic substitution reaction. Why it's called bimolecular nucleophilic substitution reaction? I will tell you in mechanism. Let's take the one simple example. Primary alkane taken. Here we'll take one nucleophile. Here primary alkyl halide was taken. Okay. Primary alkane is taken. For nucleophile, according to SN1 reaction, what first step is backside attack is not possible. Why? Because of here backside is crowding is there. pH, CH3 and AD and Cl. Here nucleophilic attack on the backside is not possible because of crowding is there. But here no crowding is there. Here also according to SN1 reaction, here no, both all are three are hydrogens only. It doesn't donate the electron density towards the carbon. Halogens have a low pair electron, but carbon around the carbon, that much electron density is not there. Why? That's why living group couldn't live outside. Okay, that's why OH group is attacking on backside. Why? Because attacking backside is free is there. So backside attack is formation to form a pentavalent transition state formation. Pentavalent transition state formation. Here nucleophile, here no crowding is there. According to SN1 reaction, crowding is happening around the carbon. More substituted group is there, donating the electrons towards the carbon, and carbon have electron density around the carbon, and chlorine have lone pairs. Electron repulsion is there. Here no donating group around the carbon. So that's why nucleophile attacking backside to form a transition state, pentavalent transition state formation. Pentavalent transition state formation. After transition state is nothing but one time only formation of breaking and making bonds. One time only is nothing but transition state. Okay, after some time carbon doesn't form a 5 valency, leaving group leave outside, form a inversion product. If you take the chiral molecule, that time only you get the inversion product. Okay, if you take the chiral molecule, that time only inversion product is formed. If you take a simple CH3 molecule, we get only simple molecule. But backside attack is there in possible in SN2 reaction. No crowding is there. That's why backside attack is possible to form a pentavalent transition state and to form an inversion product always. If you take a chiral compound only, if you take a chiral compound like this H, deuterium and tritium and chlorine is there, and nucleophile attacking on backside to form a inversion product like this, T and T. This is the chiral compound. That's why inversion product is formed. If you take a simple molecule, doesn't give any inversion product, doesn't tell any inversion product because of no chirality is there. Okay, this is all about SN2 reaction. Now we'll see what is the actual chemistry involving in the SN2 reaction. If you take an example, chiral example, deuterium and tritium and chlorine is there. We know that already carbon halogen, this is chiral compound. Because of carbon having different groups is nothing but chiral compound. Carbon halogen have a sigma bond. We know that already chemical bonding. Carbon opposite have a same type of sigma anti-bonding. Sigma star also there. Because of according to chemical bonding, same type bonding orbitals, opposite energy, anti-bonding orbitals also there. If you fill the electrons in anti-bonding orbitals, bonding order decreases. If bonding order decreases means bond length increases. Bond length increases means easily break the bond. So nucleophile come and attack to the backside. No steel crowding is there. So that's why backside attack is there. Leaving group leave outside fastly to form a pentavalent transition state. Pentavalent transition state. In that pentavalent transition state, here see the transition state. Here nucleophile is already negative charge and here also leaving group also negative charge. Here transition state increase the negative charge. In that transition state increase the negative charge. After that, leaving the leaving group and to form a inversion product like this. Inversion product. This is actual chemistry involved in the SN2 reaction. This is the one-step reaction. Okay, we will see some important points in SN2 reaction. But first point is this is single step reaction. Single step reaction. This is single step reaction. What is single step? By nucleophile attacking on backside, no crowding is there. Backside attack transition, pentavalent transition state is formation. Then form a inversion product. So this is single step reaction. Transition state is the only the rate determinant step. Okay. Second one is no carbocation formation. No carbocation formation. So no rearrangement possible. If you carbocation formation, rearrangement is possible. No carbocation formation, only transition state is formation. So no rearrangement is possible. Okay. Third point is what is the rate of the reaction? Rate of the reaction. You know that already. Rate of the reaction depends upon the according to chemical kinetics. Depends on the rate determinant. Rate determinant step is nothing but formation of this transition state. If stability of transition state increases, stability of transition state increases, rate of the reaction, SN2 reaction increases. If stability of transition state increases, rate of the SN2. If stability of transition state increases, rate of the reaction increases. Why? Because you already have a transition state negative charges increases. You decrease the negative charge of the transition state by using the summary with the time group. Rate of the reaction SN2 reaction increases. Second point is there. If you less crowding is there, SN2 crowding is there, SN2 reaction increases. If SN2 reaction is nothing but what? Attacking on backside. So backside is less crowding is there, easily attack and form a transition state and inversion product is formed. So is rate of the reaction SN2 reaction SN2 depends on inversely proportional to the steric hindrance. Okay, what is the fourth point? Fourth point is always attacking on both sides in SN2 reaction to form a inversion product. Inversion product form. Okay, this is the actually SN2 reaction. What is SN2 reaction? This is single step reaction. Backside attack, nucleophile attacking backside, no crowding is there to form a pentavalent transition state. Already transition state is nothing but making and breaking but same time is nothing but transition state. Concentrated reaction. Backside attacking is there, so that's why to form an inversion product is there. Transition state negativity charge increases. Rate of the reaction depends on stability of the transition state. If you decrease the negative charge in transition state, stability of the SN2 means rate of the reaction of SN2 increases, and what is rate of the reaction is inversely proportional to the steric hindrance. If steric crowding is there, less is there, so nucleophilic attack is fast in backside to form a SN2 reaction fastly. This is all up to the SN2 reaction. Why it's called second order reaction? Rate of the reaction according to chemical kinetics depends upon the concentration of the rate determinant step. In that SN2 reaction, rate depends upon the both alkyl halides and nucleophiles. In SN1 reaction, no nucleophile is there. carbocation is formation is the rate determinant stuff. After carbocation formation, any nucleophile, weak nucleophile, strong nucleophile, any nucleophile is attacking to form a product. But here, nucleophile is strong nucleophile needed in SN2 reaction. So, in SN2 reaction, both alkyl halide and nucleophile both are involved in the rate of the reaction. So, rate is directly proportional to the alkyl halide and nucleophile. Rate is K into alkyl halide and nucleophile. What is the order of the reaction? This is the one and this is the one. This is the order of the second order reaction. That's why it's called bimolecular nucleophilic substitution reaction. In SN1 reaction, unimolecular nucleophilic substitution reaction. It only depends upon the alkyl halides only, because of rate depends on the only alkyls only. Carbocation formation is the rate determinants of in SN1 reaction. But SN2 reaction transition state is formation. It depends upon the both and strong nucleophile and alkyl halide. So that's why this is bimolecular nucleophilic substitution reaction. This is all about SN1 reaction and SN2 reaction. I will tell you in effects also.